All right. So, so I guess that's the title. So just I'm going to talk about noisy optimization as a way to get to differentially private estimates. And this is joint work with Casey Bradshaw, who's a PhD student at Columbia, and Pauline Lowe, who's now at Cambridge. And this is sort of a summary of what we try to do in this paper. We give some global convergence analysis that holds for finite samples and for private versions of gradient descent and Newton's method. Kind of want to highlight how the theory sort of relies on local importance of local strong convexity and self-concordance for a version of the Newton's method that we use that sort of translates into good statistical performance, as I will try to point out. I think one of the practical contributions is that we identify some sort of loss functions that, combined with this framework, enables us to avoid assuming bounded data and bounded parameter spaces and so on. Try to highlight that as well. And finally, we construct asymptotic confidence intervals using this methodology. So unlike, I guess, all the other talks I've heard before, I'm going to be working with Gaussian differential privacy, but of course, we could be using something else. There's something nice about this one, and is that it's quite easy to interpret what the privacy budget parameter means. And usually once I started using this, I stopped getting the question about how to pick epsilon, because it becomes a matter of, the guarantee becomes a matter of telling apart two Gaussians, one coming from a normal 0, 1, the other one from a normal mu 1, with one random draw, right? So, and how do we get this? Will be with the usual Gaussian mechanism. So there's nothing really new there, but there's this idea again that the privacy guarantee can be kind of interpreted in terms of this sort of test of hypothesis. This is work that was published recently by Dong, Ruff, and so even though the paper has been out there for a few years now, there's a bunch of nice properties about this characterization, but the one that matters, I guess, for the purpose of this talk is that we can characterize the overall privacy loss once we do composition tightly. So if you compose k outputs that are Gaussianly differentially private, then we know exactly what the overall privacy guarantee is exactly. Okay, so that's the notion of privacy going to be working with. The sort of estimators I will be working with are M-estimators. So this class of estimators introduced by Hubert 64. So maximum likelihood type sort of estimators. So we have empirical risk minimizers. And what's sort of important to us, or I guess something I wanted to highlight, is this other version, this other way of expressing this parameter now as a solution to an equation that says gradient equals 0. So the here psi is a derivative of rho, and the reason I want to point that out is that there's this literature in robust statistics that talks about influence functions and so on. So there's this whole subset, I guess, of robust statistics that cares about constructing loss functions such as this function psi, the derivative of rho, identifies the true parameter that you care about. Okay, the true parameter theta naught, and they construct them in such a way that not only this identifies the true parameter theta naught, but also this psi function is bounded, because that in that world means the influence function is bounded, which has some meaning in terms of robustness. So there's that sort of catalog of estimators we can work with, right? So an example in linear regression is to, instead of doing least squares, do a Huber type regression. So that's what I'm kind of doing down here, except that I'm also adding, I'm not only changing the square laws to look like, quadratic and then linear, I'm also adding a downweighting function W that will be chosen in such a way so that the derivative of this loss with respect to the parameter is bounded not only in Y, but also in the X space. That's going to be important. That's what's going to guarantee that the derivative of this function is bounded both in Y and X, is bounded in our data. Okay, and if we do it in that way, then this will lead to a bounded influence M-estimator. Okay, so that's one example of how you can do this. So I said we do noisy Newton and noisy gradient descent. I'm just going to present noisy Newton, which is perhaps the one that looks a bit different from what other people have been working on in this literature. And what we do is quite simple, but we do need an additional assumption now. Not only is the gradient bounded, we also need the Gaussian to be bounded. And in fact, we're going to require it to decompose instead of this way. So we can write the Gaussian as a sum of matrices of the form A transpose, where each of those vectors now A are bounded. And this again has some kind of interpretation in the robust statistics literature from the 80s, because estimators that satisfy this sort of construction have not only a bounded influence function, but a bounded change of variance function. So people have been also proposing things like that before. And importantly, these loss functions are such that you identify the parameters we care about. Okay, then once you have that, what we do is quite simple. Use a Gaussian mechanism here on the gradient part, and you use kind of a matrix Gaussian mechanism on the Gaussian as well. And here it is crucial that the gradient, the function psi, is bounded both in the x space and the parameter space theta, which, for example, in the loss function I showed you before, that is true. Okay? Take the derivative there, that will be true, and we are writing here b and b bar as the bounds on the gradient psi and on the Gaussian function. Okay, so of course here to write two derivatives, the Huber loss would not be a nice one because it's not, doesn't have two derivatives, but you can imagine something that looks locally quadratic and then at some point it becomes linear. That is what will guarantee that the gradient itself is bounded, and that we can run this with some sort of natural bound that comes to us through the loss function as opposed to clipping. Okay, all right, so once you have this, we can give some theorem, right? So by composition and post-processing, the algorithm that I wrote down there is Gaussian is mu GDP, satisfies Gaussian differential privacy with parameter mu. So maybe I didn't insist enough here. In the terms that I have up here, I have mu and the bounds on these functions, but I also have k, the number of iterations. I need to use it explicitly when I add the noise here. So the first result is not that surprising. Then point 3 says the estimator is asymptotically normally distributed, which is, and has in fact exactly the same distribution as the usual M-estimator. And perhaps the more interesting one is the second point, where we actually just decompose sort of the error of our estimator into the usual statistical error of the non-private estimator plus the noise induced, the error induced by the algorithm, which is in fact sort of the optimal one. Okay, so what do we gain by using Newton? Well, we gain that we can use a k that is pretty small. In fact, you only need log n number of iterations to get to that rate, and you can see represented in the figure above sort of what you could expect to happen with Newton as opposed to gradient descent, right? So we know Newton's method under regularity conditions converges quadratically to the solution, and here you see the black line going down, shooting down very fast to 0, while the red one, which is the one given by noisy gradient descent, gets stuck at some point. So after 8 iterations, which this algorithm was scheduled to run 8 iterations to get 2 Gaussian differential privacy in a linear regression problem, right? It gets there, gets stuck. Its behavior is comparable to the one of, in this particular case, to gradient descent after 80 iterations. And because you have to choose k in advance, it kind of matters that you choose a small number. In fact, a lot of the, say, packages in R for generalized linear models, for example, we choose the number of iterations, maximum number of iterations to be 20. So, we are kind of in that order of magnitude. And the reason we can use, again, log n is because of local strong convexity. Without that assumption, then breaks. And in fact, here I'm kind of showing, without telling you what self-concordant is, but happy to talk about it offline. So here we kind of think of the same Huber regression problem, but we take a self-concordant version of Newton's, Huber's loss, right? And what happens here is kind of showing you what you can win by using Newton as opposed to gradient descent, because so with gradient descent and local strong convexity, you converge in log. You can use only log n steps, and so you do converge linearly, but you only do that locally. So once you're close enough sort of to the solution, then you sort of get that nice linear convergence of gradient descent. So while you're a bit off, if you're far away, it will take you you will converge quite slowly for quite a bit, and then you're gonna accelerate, whereas if you have self-concordance, you can probably, like everywhere, converge linearly. So that is one of the advantages that you have here. You're maybe a bit more comfortable scheduling a given number of iterations beforehand. And just very briefly, how would we do inference? Classically, in statistics, you would say, well, if the estimator is asymptotically normally distributed, it has some variance V. Here, to obey this so-called sandwich formula, you would plug in your estimators of theta naught, which is the parameter you're trying to estimate. You don't know it, and you're done with that. And the parameter estimate, you center it around the confidence intervals around the true parameter, and then you use the estimated variance to give you the bands. Here, that's not good enough. You can plug in our private estimators, but you still need to add some matrix Gaussian noise to, in fact, make each of the components of that sandwich matrix differentially private, and we can now, generate private versions of M. So M will be kind of the Hessian. Q would be basically the expectation of the gradient transposed, right? And so this will be Gaussianly differentially private, and we do come up with based on some argument that it's kind of buried in the proof, but there's some intuition from the proof that tells us that we should add an additional correction term. And the idea is simply that our estimator decomposes into the standard non-private estimator plus noise. So if we just use that formula for the sandwich formula, we're only using the standard parameter, non-private parameter distribution. So we take into account the fact that we add noise to it. Formula looks ugly, but it does make a big difference. As you see, the coverage of the confidence intervals for this method is the black lines if we don't add the correction. If we do add the correction, we get the blue dots, which are very close to the light green, gray ones that correspond to roughly what you get in the non-private world anyways. So you get a pretty good coverage for relatively small samples. And maybe I was a bit slow, so I'm not gonna say too much here other than perhaps this is kind of easy to implement, but it's very important in this framework for the methods to behave well statistically that you have local strong convexity or say self-concordance as algorithms that converge fast in few iterations mean less noise for your methods, right? Okay, so, and this is the reference paper. Thank you.